Alkanes are those boring organic compounds that we mentioned in the last chapter. They are different because they do not have functional groups. OH, a hydroxy group, to make it an alcohol, or an amine group, NH3, NH2, etc., or a carboxylic, C double bond OOH. Those are not found in alkanes. Nevertheless, they are still important. After all, they are the backbone, they are the foundation of that structure. Of course, reactivity is determined by the functional group, but again, we still have to take into account the structure. Alkanes are what we call aliphatic compounds or hydrocarbons. They are separated when we say aliphatic from aromatic. Aromatics are different, and we're going to study them extensively in organic chemistry 2. They only contain CH and CC carbon-carbon single bonds, and they can be cyclic or acyclic, rings or just simple chains, branch chains, etc. They have let's start with acyclic alkanes. They have the following molecular formula. It's CnH2n plus 2. It means it's double the number. For the hydrogens, they have double the number plus 2. So if we have something like C3, then H would be 2 times 3. That's a 6 plus 2. That would be an 8. So it would be C3H8, and that's, of course, propane. If you have something like a C9, then H will be 2 times 9 plus 2, which is C9H20. So that's the formula. They can contain only linear chains or branch chains. Let's look at one. So we're going to use this occasionally, these molecular representations. I'm talking about the Lewis structures, but they really become burdensome. As you notice, it takes a long time to draw them, so we need to be very good at the skeletal structures, which is what's going to be used in naming. So notice that this right here is 5 carbons. They have, again, carbon, hydrogen, carbon, carbon, sigma bond. So here's a sigma bond. Here's a sigma bond. Or, of course, they can be chained, or they can be branch chains. So this would look, by the way, like this, if we draw the skeletal structure. So you can draw your compound. Like this with a CH3. We know that the CH3 means it's a carbon with attached to 3 hydrogens. So that's 3 bonds. But for now, we're just going to show this. So you're probably going to see me, this is probably the last time I will draw things like that, because again, they take so much time, and the whole point of skeletal structure is convenience, and you'll really love them. So here's a chain, or a chain that is branched right here. And of course, if you were to draw the structure of this, it would look like you have 1, 2, 3, 4. And of course, this would be your, or of course, it could be like this. Either one is acceptable. So that would be your structure. So there's your alkanes. They are saturated hydrocarbons, Saturated means they have the maximum number of hydrogens per carbon atom. So for example, this right there, since it only has one carbon-carbon single bond, then the other three bonds have to be H. That's the octet. Whereas the one in the middle right there, it had to have only two hydrogens attached to it, and simply because it has two carbon-carbon single bonds. So that's what we mean by saturated. In fact, that's where the name saturated fats and unsaturated fat, they come from it. They come from this idea that they have the maximum number of hydrogens. Cyclic alkanes, on the other hand, they have a different formula. It's CnH2n, slightly different. So it's double the number of hydrogens than carbon. So for example, if we had the C3, it would be H2 times 3, which is 6. So that would be C3H6. C9H18, etc. And they can be joined in one or more rings. So for now, we're going to work on just a few simple rings. So the ring structure of C3H6 would look like this. It's a triangle. For now, drawing it like this. So you can count your carbons, that's 3, and you can count your hydrogens, that's 6 of them. So that's the maximum they can have. And they have less, notice, than the chains of alkanes. So you should think about why they have less. And the answer, if you thought about it, is that because they have more carbon-carbon bonds. In a ring, you end up having more carbon-carbon bonds. So you have to compensate by having fewer carbon-hydrogen bonds. So this is a ring structure. Of course, how does this look like? A nice, simple triangle. Here's cyclohexane. The H's aren't shown, but they have 2 each. So the key here is they have double the number of the hydrogens than the carbon. Of course, here's cyclopentane, etc. So all of these are existing molecules. And of course, you see this all the time in carbohydrates, fats, lipids, etc. So a carbohydrate has, for example, a 6-membered ring, or 5, etc. So what is your task? Your task is to really remember, for the acyclic alkanes, you need to remember the names of the first 10 essential alkanes. So those are the simplest alkane. So if we have one carbon atom with single carbon bonds and carbon-hydrogen bonds, that would be called a methane. Simplest gas, that's a natural gas. Ethane would be the next one. It's 2 carbons. Propane, butane for 4. That's in lighters. That's in the grilling propane. And then, of course, you have pentane, hexane, heptane, octane, nonane, and decane or nonane, decane. So make sure you memorize these. It makes no sense for someone leaving this class not knowing what a methyl group is, which comes from methane. A methyl group can tell you it's as abundant as simple, simple atoms in organic chemistry and biochem and biology, methylated, for example. So that's the idea. Now let's talk about, if we grab C4H10, it can be drawn in two different ways. We just mentioned this right here. You notice how it can be linear or branched. So there's a name for these. So again, here's C4, H10, or I could draw it this way. So if you notice here, or of course, to keep this consistent with the structure above, we'll just put the CH3s here. And of course, there's an H. We don't show the H. So this, you should be able to compare this to that. So both of these satisfy the octet rules for this molecular formula, but there's a name for these. Of course, there's a difference between them. So these are what we call constitutional or structural isomers. We mainly use constitutional isomers, but in case it's used interchangeably, it would be called structural isomers. They're compounds with the same molecular formula, but different structures, meaning the connections are different between the atoms. So for example, C in this case, the one in the middle, is attached to 3 carbon atoms versus, if you notice, the ones in the middle here are only attached to 2, etc. And these are called constitutional isomers. So for example, here's another constitutional isomer. You may not be able to see it, but this and that, you should check. They actually have the same molecular formula, etc. Now, what you should be doing, and we're going to check when we come on the next session on Thursday, you should be doing this. You should be able to draw for C6, H14, hexane. You should be able to draw the different constitutional isomers. There are different ways, as long as, remember, to satisfy the octet rule. You cannot draw these and violate the octet rule. So work on these, and then, of course, we'll check the next time we meet. Alkanes with straight chains are called N-alkanes. N is for normal. So if you notice here, these are straight chains. We call this an N-alkane. And since we have 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, we call this N-pentane. Normal, N for normal. Although sometimes, most of the time really, if it's a straight chain, that N is removed because it's implied. However, if you have a branched alkane, you should be able to give one example, like maybe the one from the cyclohexane. This would change. So this now, again, has the same molecular formula. That would be a C5H12. And we have 12 hydrogens, if you count them, same as here. These are, if they are branched, you use iso. Iso is used for some, especially the majority of them, the important ones. So in this case, we have 1, 2, 3, 4, 5, but again, it's a branched, there's a branched here, it's a branched pentane. So we call this an isopentane, but the technical name, and we're going to talk about the name, is 2-butane, 2-methylbutane. We will talk about this, but this would be an isopentane.